All right, so Chem 30, we're starting Materials Science Unit Section B. This is the second section. We did Section A. This section is largely the organic chemistry section. We first start off with valence shell electron pair repulsion model theory, okay? Coming to you from Glencoe Chemistry Textbook, chapters 8, 21, and 22. So we're going to start with, in the section chapter 8, and we're talking about VSEPR. Now, it's kind of spelt VSEPR. I think you'll hear it a lot of times just VSEPR, just for ease of saying. But this is, of course, the acronym for Valence Shell Electron Pair Repulsion Model. So this is how we get the shapes of our atoms. This is where we get orbitals from. This is where we get bond angles and those sorts of things from, is from this theory right here. So, in your notes in front of you, you should have notes in front of you that will have some blanks that you can fill in. This is the opener here. It says, so far we've used Lewis structures to account for formulas of covalent compounds. Now, we haven't done a whole lot of that. You know what Lewis structures are. We did a little bit of this. So, Na has a one, lone electron there, and Cl would have, 7 valence electrons. And these guys get together because this electron here, right, is stolen by chlorine for an outer, full outer electron shell, and therefore this sodium is positive, chlorine becomes negative, and boom, they come together. Now, the Lewis dot structures help us to understand sort of, why that happens. But the one problem with Lewis structures is that they do not show the shapes of molecules. They simply show the number and types of bonds between the atoms. So when we draw Lewis structures, it shows atoms in the same plane, but the arrangement of the atoms in reality is three-dimensional. So this is why we need to talk about the three-dimensional valence shell electron repulsion theory here. So the CH4 molecule, okay, we did talk a little bit about the CH4 molecule in the previous class. If we have a carbon here, and we have a hydrogen in this plane, and let's say we have another hydrogen in this plane, the other two hydrogens, if we're drawing a 3D structural formula, it becomes a little tricky to draw that two-dimensionally, okay? And I don't know, did you guys see this video, the revolving sort of 3D, okay, structure? Okay, so this video, the VSEPR animation, kind of shows you the 3D formulas, so you can watch that video if you haven't seen it yet. But in drawing these things, it becomes a little tricky to show. Now down here, now we understand that one kind of hydrogen goes back into the screen there, and one hydrogen comes out in front. Okay, so how we draw that is tricky on a two-dimensional plane, and we'll talk further about how we actually do this a different way. But what I want to get into is to try to show you, and of course this chart right here is where we want to focus on understanding the shapes of molecules with different types of numbers of bonds and stuff. So you may have seen this chart already, and I think for some of you in my class, this is just a review part. So you have done this, you should have this in your notes. But when we have a molecule where we have two electron-dense areas. Now, let me explain this. Electron-dense areas are either bonds or they are lone electron pairs. In any case, they have two electrons, and we've got some kind of repulsion going on here. We've got some kind of orbital. We've got space that it has electrons in it. And so if we have two electron-dense areas, there's only really one option. And that is a linear shaped molecule, okay? 2 electrons. There's no electrons up here. There's no electrons anywhere else, just the 2 shapes. So that one's pretty straightforward. It's linear. All right, so what if we have 3 electron-dense areas? So this is either 3 bonds or 2 bonds and a lone pair of electrons. If we have 3 bonds, so that means we have an atom here bonded to 3 other atoms, then this will spread out in 3-dimensional space, just like sort of like a peace sign or something. Like they'll all be spread out exactly the same distance apart in space, and they'll all be on the same plane. Okay, they'll all be on the same plane. We call this trigonal planar. Trigonal planar. Linear trigonal planar. Now this is interesting. If we have just 2 bonds between atoms and 1 lone electron pair, we have a molecule that is bent. All of these are still in the same plane, okay? Same plane, but we still have a bent molecule now because you don't really count this lone electron pair. You only count the atoms that are in the molecule. So this is bent. And why is it bent? Well, if we have a lone pair of electrons, you can understand that they will act similar as another bond, and they will literally push the other atoms and the other electron dense areas away. So they will want to spread out, but it'll only look like it's a bent molecule. Yeah, question? Yeah. Okay. So these. So again, this is an electron pair that is not involved in bonding. So this atom right here is not bonded to anything else over here. This is the case where we have a lone electron pair, and there are lots of molecules that you're going to find out here in organic chemistry where some of these electrons are stuck to the kind of the center atom here, but they're not actually bonding with anything. They're just lone pairs of electrons that they're not bonding with anything, especially if this has the two electrons. This orbital is already filled, so it's not looking to bond with anybody. You know, it depends on the nature of the compound. And how do you express it? You express it just like this. You just draw a little kind of bubble with two dots in there, and that's your lone electron pair. Okay, so if you were to draw that. But I guess the point is, the reason why we call this a bent shape molecule is because we're only considering the atoms in the molecule, okay, for the shape. The lone electron pairs do not contribute to the shape. All right? Only the bonds with atoms on the ends of the bonds, those are the ones that you consider for the shape. That's why this is trigonal planar. That's why this is only bent. Okay? Because we're only considering these three things right here. Okay, good. Any other questions there? Oops, those are good questions. Let's keep moving on. So what happens if we have 4 electron dense areas? And again, the nature of this center atom will dictate how many electron dense areas we can have. Either the number of bonds it can form, the number of lone electrons that are there. So if we have 4 dense areas, they will spread out in space exactly the maximum distance away from each other, and we have something called a tetrahedral shape. So if there's a center atom, and if we have atoms bonded at the end of each of these bonds, then we consider all of these atoms in the shape. It's called tetrahedral. Tetra is 4. Tetrahedron would be a 3-dimensional shape, a tetrahedral shape. Okay? Now, if it's the case where we have a molecule that not all of the electron dense areas are actual bonds, where we have one lone pair of electrons, okay, then this is a trigonal pyramidal shape. So again, we only consider the atoms in the bond. So that means we would consider this one, this one, this one, and this one back here. So it's a trigonal, which is like tri is 3. A pyramid would have a solid base, and it would come to a point. A pyramid always comes to a point. So if you consider this trigonal pyramidal, it would be like this. We've got a triangle on the bottom, and we've got we've got 3 other triangles here. Trigonal pyramidal. The electron pair that's out kind of loose out in the open is up here, but it's not considered in the shape. So that's why it's a trigonal pyramidal. This is a triangular pyramid. Okay, trigonal pyramidal. Now this one is interesting. What happens if we have 2 bonds and 2 lone electron pairs? Well, again, if we just consider the atoms involved, we have a bent molecule again. Okay, so in 3D space, it's really indistinguishable from this one up here, this bent. But there are 2 lone electrons. So I know you guys have asked before, so when does this happen? Well, this one is actually the water molecule. This is what happens with a water molecule. So if we have an oxygen, okay, and 2 hydrogens here, right? The hydrogens only have 1 electron to contribute to this molecule. How many electrons does oxygen have in its outer shell? Well, I'm going to count the second row. 1, 2, 3, 4, 5. It has 6. So let's go 1, 2, 3, 4, 5, 6. Notice that a bond contains 2 electrons. We have a bond there and a bond there. And the oxygen has 2 pairs of lone unbonded electrons. So what that looks like is this right here. It's a bent molecule. A little tough to draw it in 3D space, right? But that's why the molecule looks like this. You have this big oxygen atom with these little hydrogens, right? Kind of like that. It's a bent molecule. There to there. And what you don't see is the electron clouds that are forcing these bonds away from themselves. One of these electron clouds is kind of coming out of the screen at you. Boom, 2 big electrons. And one is kind of in the rear there, okay? 2 little electrons. One's coming out, one's going back. So we do have to think about this, 3-dimensionally. That's the best way to do this. Okay. Oh, I've got that shut off. Okay. Any questions here so far? So what if we have 5 electron dense areas? No problem. That could happen. 5. Now, of course, we could have 6 as well, so this is where we're going to stop. But 5. All right. So if we have 5 electron dense areas, that means we have to spread out 5 bonds into 3-dimensional space. And what we end up having is something called a trigonal bipyramidal shape. Trigonal bipyramidal. So you want to think about this, and this is a good representation. Okay, this is a good representation here. If you can kind of see what's happening here, these 4 right here would all be in the same plane, the plane of the board there, the plane of the screen. These 2 atoms, one is coming out at you, and one is going away from you. Okay, so that one's coming at you, one's going out back behind. And so this is a 3-dimensional representation. And if you notice the whole trigonal pyramidal thing right here, so again, there's our triangle that's in the middle plane, the plane that is horizontal coming in and out. And then we have a pyramid on top, and we have a pyramid on the bottom. It's bipyramidal. 2 pyramids, one on top, and then one flipped around, stuck to the bottom. Trigonal bipyramidal. Okay, that's the shape of the molecule if all of the electron dense areas are bonds. All right. So what happens if this center atom is only able to bond with 4 others, and there is one pair of electrons that's causing, a push, a repulsion against the other ones? Well, we still have this same shape if you consider all of the electrons involved. However, in actually naming the shape, we only consider the atoms that are involved in bonding. So what does this look like? Well, if you tilt your head sideways, it kind of looks like a seesaw, or what they call it is a sawhorse. So a sawhorse is an old carpentry term. And it's basically if you have a platform like this and you have 2 kind of stands like this, that's a carpenter's sawhorse there. And you put something on here and you can whatever. Now this, if you turn your head sideways, here are the legs of the sawhorse, and here's the plank on top. Okay. Or think about it as a seesaw. Okay, a seesaw here's my stick kid. Okay, hanging over there. And here's the other one. See, turn sideways. You can see this. There's a kid hanging there, holding on. It's a seesaw or a sawhorse. Seesaw, sawhorse. Got it? If you consider only the atoms involved, that's what it looks like. Well, this is more like a seesaw, but they call it a sawhorse. I'm not sure seesaw. I don't know when they named this. They didn't want to use seesaw, or seesaw was not really a common term that maybe we know of. But that's what you want to think about it. Okay, you getting it? So the big thing is to remember that if there's 5 electron dense areas, some of these will have atoms at the end of these bonds, and some of them will just be free pairs of atoms in space, but they're all kind of pushing on each other. So that's why this is all in the same row, the 5 electron dense areas. Count them. Here, 1, 2, 3, 4, 5. Over here, 1, 2, 3, 4, 5. Over here, 1, 2, 3, 4, 5, and so on. It just so happens that some of these electron dense areas do not have bonds attached to the ends of them. Sure. Put it right there. Thank you very much. Okay, so moving on quickly here, sawhorse, yep, T-shaped. Okay, so what happens if we only have 1, 2, 3 in a row, and then this one of these pops out here? Well, that's a T, literally. If you were to look at this, if you were to think three-dimensionally, if you were to flip it around, this is what we have right here, all in the same plane. That's a T, makes a big fat T. Okay. And then finally, if you only have 3 atoms involved, and 3 lone electron pairs, they are all going to spread out and repel each other, and you're going to have a linear shape. Okay, a linear shape here, straight line. It's not going to be bent because if you think about this, here's an atom, here's an atom, here's an atom. Why would these two be together if we have, 1, 2, and 3 of these out here? No, these electrons here are big and repulsive. So these are going to spread out. These are going to want to spread out from each other more so than these. So these are the priority, the electron dense unpaired electrons. Those are the big bullies in the room. So they have to spread out first, and then these ones will fill in the occupied space. So that becomes linear. All right. All right, one more line to go over here, and this is the 6 electron dense areas. This is octahedral. Okay, so octa is 8. How do we get 8 out of this? How do we get 8 out of this? Anybody know? Like, why is it octa anything? 8 surfaces. Yes. 8 surfaces. Okay, you're going to say that too? Okay. Okay, awesome. Okay, so let's see. Here's one. There's one surface right there in the front. Here's a second. There's a third in the back. And here's a fourth on the side. If you flip that upside down, you've got 1 back here, 2, 3, and then the front one is 4 as well. So that's 4 and 4 is 8. That is an 8-sided surface, absolutely. Okay, so if you have an atom bonded to 1, 2, 3, 4, 5, 6 other atoms, then you have an octahedral shape molecule there. If you have 1 electron dense area that's unbonded, and you only have 1, 2, 3, 4, 5, 6 atoms here, then this is a square pyramidal. Now you have to turn your head sideways and look at the square right here. That's a square. It's in the plane, the up and down plane. And then of course there's one more atom out here that kind of comes to a point. Therefore it's a square base, and I'll draw it again down here. It's a square base pyramid. Okay, square base pyramid. So it's square pyramidal. Can you what? Yeah. Okay, if you have 2 electron dense areas, then this is just square planar. Okay, it's all in the same plane. There's your square. Again, we can have a T shape, and of course we can have a linear over here on the side, linear as well. So again, in counting the shapes of these molecules, you only consider the atoms, not the unbonded lone pairs, but they do contribute to the shape. But in naming it, you have to just consider the atoms that are involved. Okay, organic chemistry is the branch of chemistry dealing with compounds of what? Who might know this one? Compounds of? Carbon. Carbon is correct. Carbon. Carbon, okay? So, yeah, molecules, compounds that are carbon-based are the primary focus here of organic chemistry. So, naming basic, simple, excuse me, organic molecules, page 750 of your Glencoe here. We're going to quickly go over this chart here. Naming these, this is very, very important, extremely important for the rest of organic chemistry. You need to know that one carbon atom in a simple organic formula that's carbon with 4 hydrogens is methane. Methane. Okay? Very important. Meth. Think of meth, methane. CH4. And of course, the 3-dimensional drawing would look something, like this, okay? Where you have one kind of coming out at you and one kind of back towards the back. And this is the way it's sometimes written in organic chemistry too, with like kind of a wedge, a solid wedge here. It's coming out at the board. And then a hatched sort of wedge that signifies kind of going back into the screen there. All right. So that's also, you'll see that sometime as well. 2 carbons is ethane. And we have carbon, I won't draw 3-dimensionally for these now, but 2 carbons, they also should have a full octet around them, 4 bonding, 4 electron dense areas, and if it is completely saturated with hydrogens, as this is, then you would have 2 carbons and you'd have 6 hydrogens. That's ethane. Propane is the next one. Meth, eth, prop. Meth, eth, prop. Have to remember that. And that's going to be C3. How many H's are going to be attached there? Well, let's see. We have 1, 2, 3 on this end, 1, 2, 3 on this end, and then we have 2 more in the middle. So what's that? C3H8. Awesome. So 3 carbons in a simple organic straight chain molecule is propane. And yes, this is the same propane that you burned when you're doing barbecue. Okay, I did barbecue yesterday. Turn on the propane, burn some propane. Okay, what do you get when you burn a hydrocarbon? If it was pure propane, what would be the result of that? We learned that early on in the course and last year as well. What kind of reaction is that? It's combustion. Yes. What are the products of a combustion reaction? Carbon dioxide and water. Awesome. Yeah, and obviously heat, right? And heat as well. But for products, carbon dioxide and water. Interesting. So propane, yes. So meth, eth, prop. The last one is, well, not the last one, but the really important one here is bute. Meth, eth, prop, bute. Butane. C4H10. And then your hydrogens there. Yeah, question?
What do you even use that for?
Well, butane is a fuel that you can burn as well. You ever heard of a butane lighter? Yeah, a little butane lighter, lots of heat, and it burns butane. Lighter? Yeah, it's like one of those little ones. Yeah. It's kind of almost like a little torch, you know? Little torch, butane lighter. Yeah. Okay, so yeah, I mean, and we'd put hydrogens in all these. Okay, so we'll finish up with 5 and 6. 5 would be, any guesses what the prefix for 5 would be? I think you guys should have this in your notes, right? Pentane is correct. Pentane, C5H what? What do you think? What are we going to have here? What's the pattern here? Thank you. C5H12. Okay, and yeah, you can draw that as well. So what you want to notice in these simple straight chain, simple organic molecules that we're studying here is that for each addition of a carbon, see, like if we go from 2 to 3, what are we adding? 1 more carbon and 2 more hydrogens. We're adding 1 more carbon and 2 more hydrogens. 1 more carbon and 2 more hydrogens. So we've got a pattern going on here for these simple straight chain organic molecules. Okay, finally, penta, what's going to be 6? Sorry? Not oct. Octane is a thing. If you drive a car, if you've ever put fuel in your car, the octane level, yeah, there's octane as well, but this is, right, I heard it, hexane. Hexane, hex, C6H14. Simple straight chain organic molecules. Now I say straight chain because we'll find out here soon that these molecules can actually wrap around into a circle, some of them. There can be more than just a single bond. We can have other types of bonds, which will change the way we name it. Okay, so right now, simple straight chain organic molecules, meth, eth, prop, bute, penta, hexa, all that sort of stuff. You need to memorize those prefixes. And then notice that each of these have an A-N-E at the end, A-N-E. So simple straight chain, single bonded organic molecules like this will end with ane. Okay? So meth, eth, prop, bute. Super important. I cannot stress that enough. Meth 1, eth 2, prop 3, bute 4. You need to memorize that. You'll come back to that many, many times. Okay, let's continue on. What I just mentioned was naming. So you can name things different ways. Compounds that contain only single bonds okay, between carbons are called saturated compounds. Saturated. Which really means that every available bond position is filled with a bond. We will find out that unsaturated means that there would be double and triple bonds. And so that means that every electron pair does not equal one single bond. But these are saturated, okay? So there's as many hydrogens as possible. And this group is called alkanes, and that would include the ones that we just learned about, propane, ethane, hexane, and all that. Octane, decane, all that. Saturated. All right. If a double bond exists, a double bond, that's between carbons, of course, because hydrogen can't form double bonds, right? It only has one electron to give, so it's only maximum a single bond. But if there's double bonds between carbons, the compound name ends with -ene. This is the one slight difference for a doubly bonded compound, okay? And of course, in a triple bond, we have a different name, and that is the name that ends with -ine. So we change the suffixes to -ene and -ine, okay? And of course, these, not in the notes, but this group is called alkenes, and this group is called alkynes. Okay, that's sort of the group name for, doubly bonded and triply bonded. So there's a couple examples that I have here. I'm not sure if you have those in the notes in front of you or if you had to fill those in. But ethyne, okay, so why is this ethyne? Two reasons. There are two carbons, and so that's where we get the eth from. Remember? Meth, eth, prop, bute. Meth, eth, 2. It has a triple bond. Okay, so a triple bond looks like 3 lines in between the carbons, each line representing a pair of electrons involved in a bond. So if there are 3 lines there, that's a triple bond. Yeah, pretty crazy. If you were to draw that out a different way, it would look sort of like this. Electron, 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 electron. And we've got then 2 electrons over here with the H and 2 electrons over here with the H. Okay? So this is a triple bond. Now, why are there not more H's? Why are there not more H's here? Anybody would know why there are not more H's? Why would this not look like this? Yes. Because what? They what? The electrons? Yes, these electrons, exactly. These electrons here are represented in the middle. Carbon cannot have all of these electrons around it, okay? This is not cool, okay? That's way too many. That's more than the octet. There would actually be 2 more in here. So this would not be cool. 1, 2, 3, 4, 5, 6, 7, 8, 9. No good, okay? And even these actually would be considered, I should say. So that's way too many. So it does not have these bonds here. Let's check why you would not include those at all. It's because carbon here has, okay, oh, I gotta get rid of this too. It has 2, 4, 6 right here, and then 8 right here. So it has a full octet there. It does not have any more chances or spaces or sites to bond. No more electrons to give. They're not digging electrons out from a lower energy level there, just the valence ones. So, and that's the same case, of course, for the other carbon as well. It has 6 electrons around it. There's a triple bond here, and then 1 more single bond. Okay, this one here, meth, eth, prop, bute, that's 4 carbons, and it's a double bond that we see in there. So this is butene. Butene, okay? We will have a better, even more detailed name for this coming up, okay? Because this one, there's actually different varieties of this butene that we will see. But just so you know that where this comes from, the bute is from the 4 carbons, and the ene is from this double bond that we see right there, okay? If this was a single bond and we had an H over there and an H over here, this would just be butane. Butane. But because we have a double bond, it's butene. Got it? Questions? All right, as I mentioned earlier, we can have some longer chains that could actually kind of circle around, and carbons could bond obviously to each other in a straight chain, but the carbons on the end could actually kick off, a couple hydrogens and bond to each other to make a cyclo, a circle, a chain, a circle compound, which is cyclo. So what we have to do to name these is add cyclo here as a prefix. Okay, pre means coming before. So this right here is 1, 2, 3, 4, 5 carbons, and because it's got all single bonds between the carbons, and it's in a circle. Now I know this is looks like a pentagon. Okay, that's how you draw them, but because the ends are attached to each other, it's called cyclo. Okay, and this is called a cyclopent for 5, and then ane for the single bonds, cyclopentane. And as we move further and further into these organic molecules, the naming becomes quite complicated. It does. But we're taking it one step at a time. You have now 3 bits of naming that you understand now. So this is all going to come in a natural progression for you, okay? So any questions about this page here? Alkanes, alkenes, alkynes, what they represent, and what the cyclo means? Yeah? No. Hello. All right, cyclopentene, as you might understand, cyclo is going to mean that the ends they're all hooked up. So this is not a straight chain like this, C, 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 5. It's not straight. This carbon over here is bonded with this carbon to make a cyclo, okay? Pent, we have 5. But the ene here, notice the ene means that there exists at least one double bond. So we have a double bond represented between carbons, and that's what this looks like. Now, I mentioned the sort of the condensed structural formula, okay, or sort of it's just a bare structure. You won't always have to draw all the hydrogens, and pretty quickly here you can kind of see that drawing the hydrogens is going to be quite onerous. It's going to be quite a big deal. So you will see this in the textbook, and I'll be drawing it like this as well. We drop really, for organic chemistry, it's assumed that at each corner, at each point here, there's a carbon. And the lines between those corners are bonds. And so with this one here, you can see that we have 5 carbons and 1 double bond. There's 2 lines here that represents a double bond. So you might see this cyclopentene start to look like this in your textbook and in the notes. Okay? So cyclic hydrocarbons are called cycloalkanes if they have single bonds only, cycloalkenes containing a double bond, and cycloalkynes containing triple bonds. So we want to reinforce the anes, enes, and ines, and also the cyclo. So that's going to be a prefix at the beginning. Don't put it at the end. Not pentene cyclo. It's cyclopentene or whatever. Okay. All right. Any questions at this point? Okay. Okay, hybrid orbitals. We've talked about orbitals, right? We've talked about the fact that surrounding a nucleus, we would have, an s orbital, spherical, right? We could also have p orbitals, which would be sort of hourglass shaped, that would extend into space like this with different lobes, okay, in the back there, and then one big fat one coming out front. So we've talked about s orbitals, p orbitals. They're obviously, as we go further down the rabbit hole here, things get a little bit more complicated, and with your study in the last section about quantum physics and quantum chemistry, we understand that things are not as simple as it seems. So we've got s orbitals, we've got p orbitals. We understand those really when we're talking about simple, small atoms, but at parts of the periodic table, and I'll show you, let's go back to the periodic table here somewhere. Oh, there we go. That's the wrong one. Periodic table. Nope. Come on. There we go. So the periodic table here, obviously these s, p, d, f orbitals are all based on one single electron given enough energy, and they watch and see where it goes. They do the math and calculate where this one would go. So they're assuming, really, that a bunch of electrons in a larger atom would fill the orbitals that are predicted through hydrogen. However, when we get to this area over here, it starts to get a bit fuzzy. And part of the reason why we have multiple oxidation states, which you don't know what oxidation states probably mean, but multiple ionic charges, is because the orbitals start to morph a little bit. So the straight S, the straight P, the straight D, they start to melt together a little bit, and it gets a little complicated. So I'm going to try and break that down for you here now. Where did we go? Okay. So hybrid orbitals. At times, overlapping orbitals morph into a special kind of orbital called a hybrid morbital. Morbital. It's very sad and deathly. Morbital. An orbital. The name is just as it suggests. It's a combination of two or more orbitals, okay? Hybrid. This occurs often, but we will focus on one type of hybrid orbital called the sp3 orbital. Wow. You thought there was just S's and P's. Nope. There's an sp3 orbital too. These orbitals form in carbon, allowing 4 possible bonding domains. Okay, so think about carbon. I mentioned the transition metals, but think about carbon. This is where we see it first, and this is the one we're going to study, really. Carbon normally has 2 electrons in the 2s orbital. Okay, so remember our orbitals here. There's hydrogen, there's helium, there's lithium, here's beryllium. So carbon is over here somewhere, right? Right? Carbon's over here somewhere. So in the 2s orbital, let me just finish this thought here. In the 2s orbital, we normally have 2 electrons here. Got electron there, 2 there. And 2 in the 2p. 1 here, 1 there. 1 filled orbital, 2 half-filled, and 1 empty. But in reality, there are 4 half-filled orbitals that are formed. So 1 s orbital plus 3 half-filled p orbitals actually forms something called the 4sp3 orbital, and there's 4 of them. This is what gives carbon its tetrahedral geometry, the tetrahedral geometry. Okay, we'll continue this lesson next day.